Identifying max and mins. First you get your critical point. Critical point, let's just do maximums, minimums will be the same. So in 3D, it looks like a maximum in every direction. So now our parameter space is the xy plane. So we can think of those points being lifted onto the surface into curves. We then have tangent vectors. Since it's a critical point, the slope is 0 in every direction. Horizontal tangent plane, horizontal tangent vectors. Definition for critical point then is one where both partials are 0. Because if both partials are 0, then no matter what direction you're looking at, the directional derivative is 0. Now that you have a critical point, we need to test it. In the parameter space, this is the picture we're looking at. The t value where we have slope 0. But that is the directional derivative at the xy point. Plugging in the parameterization. And the two different notations for directional derivative. Calc 1 is the second derivative at the critical point is negative, then you have a maximum at that t value. That's the t derivative of the t derivative. But taking a t derivative is u dot the gradient. Filling it in. And now we just need to expand the symbols. There's our u dot the gradient of u dot the gradient. U is a constant with respect to the x derivative. Take an x and y partial. As long as f is smooth, it doesn't matter what order you take those partials, you get the same answer. So we can collect them together. This quantity is the second t derivative. If that is negative for all directions, we're at a maximum. As a function of u, it's a quadratic. In particular, as a function of u1, it's a quadratic. So we want to complete the square. So we do this algebraic form on the above equation. Pull out the second x derivative. Rearrange to make it look like this algebraic form. So u1 is my x, there's my a, there's my b. So it's the second x derivative, a square term, and a term with uncertain sign. So let's look at that term more closely. get a common denominator and factor out the common denominator. Alright, so now it's the second x derivative times a positive term. B minus a squared, positive term, positive term. So if this is also a positive, then my second x derivative has the same sign as my second partial derivative in any direction. So both max and min are covered with this case. If the sign of that term we're looking at is a negative, then for some u, the term in brackets is negative, and for some u, that term in brackets is positive. So for some directions it has a maximum shape, and for some directions it has a minimum shape. Putting those together at the critical point, the shape is a Pringles potato chip shape. Or, because calculus is old, it's a saddle point. To recap, you get your critical point. That's where your gradient is 0. 0 vector. That means both your partials are 0 at the same point. Then you test your critical point with your second derivative test. The term that determines whether you have max mins or not is called the discriminant. So if your discriminant is positive, then the sign of the second x partial determines max or min. If your discriminant is negative, it's a saddle point. And if it's 0, it just means your test fails to classify. And you have to use other methods